Well, welcome back to our journey through the TCP/IP model. We have been in Unit 3 for some time, and we are still in Unit 3, which is a study of the transport layer. In the last few lessons, we have been discussing the problem of reliable data transfer. Essentially, how does the transport layer guarantee that the data makes it from source to destination system without having the message distorted, bits dropped, or totally lost? And in the process of that, we examined the stop and wait protocol and selective repeat protocol and go back in protocol. Now we're going to move on to the next issue, which is TCP, Transport Control Protocol. So let's pick up where we left off. TCP is the transport layer's connection-oriented reliable transport protocol. We'll see that in order to provide reliable data transfer, TCP relies on many of the underlying principles that we have been discussing, including error detection, retransmission, cumulative acknowledgments, timers, header fields for sequence and acknowledgment numbers. TCP is said to be connection-oriented because before one application process can begin to send data to another, the two processes must first handshake with each other. That is, they must send some preliminary segments to each other to establish the parameters of the ensuing data transfer. As part of TCP connection management, both sides of the connection will initialize many TCP state variables associated with the TCP connection. The TCP connection is not an end-to-end time division multiplexed or frequency division multiplexed circuit as in a circuit switch network, nor is it a virtual circuit, as the connection state resides entirely in the two end systems, not the core of the network. Because the TCP protocol runs only on the end systems and not in the immediate network elements, the intermediate network elements do not maintain connection state. A TCP connection provides full duplex service. If there is a TCP connection between process A on one host and process B on another, then application layer data can flow from process A to process B at the same time as application layer data flows from process B to process A. That's full duplex. A TCP connection is also always point-to-point. That is, between a single sender and a single receiver. In other words, full duplex data can flow in both directions at the same time. Multicasting, the transfer of data from one sender to many receivers in a single send operation, is not possible with TCP. Let's now take a look at how a TCP connection is established. Suppose a process running in one host wants to initiate a connection with another process in another host. Remember that the process that is initiating the connection is called the client process, while the other process is called the server process. The client application process first informs the client transport layer that it wants to establish a connection to a process in the server. TCP in the client then proceeds to establish a TCP connection with TCP in the server. The client first sends a special TCP segment. The server responds with a second special TCP segment. And finally, the client responds again with a third special segment. The first two segments carry no payload, that is, no application layer data. The third of these segments may carry a payload. Because three segments are sent between the two hosts, the connection establishment procedure is often referred to as a three-way handshake. Once a TCP connection is established, the two application processes can send data to each other. Let's consider the sending of data from the client process to the server process. The client process, the application, passes a stream of data through the socket. Once the data passes through the door or socket, the data is in the hands of TCP running in the client. TCP directs this data to the connection's send buffer, which is one of the buffers that is set aside during the initial three-way handshake. From time to time, TCP will grab chunks of data from the sender buffer and pass the data to the network layer. This all should be sounding pretty familiar. The maximum amount of data that can be grabbed and placed in a segment is limited by the maximum segment size. Hopefully you remember from our previous lessons that each layer has its own protocol data unit, PDU. The transport layer has the segment and the data link layer has the frame. The maximum segment size is typically set by first determining the length of the largest link layer frame that can be sent by the local sending host. This is called the maximum transmission unit, or MTU. Then the maximum segment size is set to ensure that a TCP segment, when encapsulated in an IP datagram, plus the TCP IP header length will fit into a single link layer frame. Both Ethernet and the PPP link layer protocols have a maximum frame size of 1500 bytes. Approaches have also been proposed for discovering the path maximum transmission unit, the largest link layer frame that can be sent on all links from source to destination, and then setting the maximum segment size based on that path maximum transmission unit value. Let me clarify just a little more. The single link, the connection between a host and its neighbor, has a unit value. But in an internet connection, there are usually many links between the client and server. That's what we're referring to as the path. Note that the maximum segment size is the maximum amount of application layer data in the segment, not the maximum size of the TCP segment including headers. This is confusing now, but it'll become clearer as we proceed. TCP pairs each chunk of client data with a TCP header to make up TCP segments. The segments are passed down to the network layer where they are separately encapsulated within network layer IP datagrams. The IP datagrams are then sent into the network. When TCP receives a segment at the other end, the segment's data is placed in the TCP connection's receive buffer. The application reads the stream of data from this buffer. Each side of the connection has its own send buffer and its own receive buffer. We see from this discussion that a TCP connection consists of buffers, variables, and a socket connection to a process in one host, and another set of buffers, variables, and a socket connection to a process in another host. As mentioned earlier, no buffers or variables are allocated to the connection in the network elements, the routers, the switches, and the repeaters, between the hosts. And let's examine the TCP segment structure. The TCP segment consists of header fields and a data field. The data field contains a chunk of application data. As mentioned earlier, the maximum segment size limits the maximum size of a segment data field. When TCP sends a large file, such as an image, a video, or something like that, as part of a web page, it typically breaks that file into smaller chunks at the maximum segment size, except for the last chunk, which will often be less. Interactive applications, however, often transmit data chunks that are smaller than the maximum segment size, for example with remote login applications. The data field in TCP is often only 1 byte. Because the TCP header is typically 20 bytes, 12 bytes more than the UDP header, segments sent by login may only be 21 bytes in length. Figure 3.29 shown here shows the structure of the TCP segment. As with UDP, the header includes source and destination port numbers, which are used for multiplexing or demultiplexing data from or to the upper layer applications. Also, as with UDP, the header includes a checksum field. A TCP header also contains the following fields: the 32-bit sequence number field and the 32-bit acknowledgement number field are used by the TCP sender and receiver to implement a reliable data transfer service. The bit receive window field is used for flow control. It is used to indicate the number of bytes that a receiver is willing to accept. The 4-bit header length field specifies the length of the TCP header in 32-bit words. The TCP header can be of variable length due to the TCP options field. Typically, the options field is empty, so that the length of the typical TCP header is 20 bytes. The optional and variable length option field is used when a sender and receiver negotiate the maximum segment size or as a window scaling factor for use in high-speed networks. A time stamping option is also defined. The flag field contains 6 bits. The acknowledgement bit is used to indicate that the value carried in the acknowledgement field is valid, meaning that the segment contains an acknowledgement for a segment that has been successfully received. The RST, SYN, and FIN fields are used for connection setup and teardown. Setting the PSH bit indicates that the receiver should pass the data to the upper layer immediately. Finally, the URG bit is used to indicate that there is data in this segment that the sending side upper layer entity has marked as urgent. The location of the last byte of this urgent data is indicated by the 16-bit urgent data pointer field. TCP must inform the receiving side upper layer entity when urgent data exists and pass it to a pointer at the end of the urgent data. In practice, the PSH and URG and the urgent data pointer are not used. The purpose of the encapsulation process of a layer protocol like TCP is to include enough instructions with the bits received from the layer above to allow its peer on the other end to pass that data up to the layer above as it was originally sent by the source peer. As you can see, the packet contains all of the instructions needed to guarantee that the data is received as sent, which is the primary purpose of the transport layer. Let's take a break right here. As you'll be able to see, this particular unit is going to contain more than one lesson. Look over your notes and the study guide and the notes you've made on the study guide, and then when you're ready, come on back and we'll proceed to the next lesson.